Hello there. So you're a chemist and you've been given this bowl of white solid substance. You are asked to identify it. Now, a chemist equipped with all the right tools should be able to decide exactly what that is. But seeing as there are thousands of possibilities for what could be a white solid, we need ways to narrow it down very quickly. From what we've done in this class so far, hopefully there's one technique that comes to mind right away, and that would be melting point. But still, lots of other white solids could have overlapping melting point regions. So that's certainly not sufficient. We, at the end of covering all of our what's called the spectroscopy units, we will be able to come up with ways to conclusively tell the person who's asking us this question exactly what the structure is of this white solid. So today's goal will be to get comfortable with how IR, infrared spectroscopy, could help us get closer to solving the mystery of what a structure could be. So first, I'm going to put this little unknown over there. We're going to kind of do an overview of all the spectroscopies you'll be learning and what that really means. So spectroscopy is a type of instrumentation technique that uses light as the energy source to pass through one of our samples, and the very crude sort of simplified definition that could kind of apply to them is if you have your sample and you're able to, let's say we have this sample here, and we're able to pass light through it, and light has an energy, right? So energy of light, h nu for the photon. So light in passes through the sample, and the sample, we would only use light that the sample would actually partially absorb, because that would give us interesting information based on how much it absorbs. So the sample would retain some of the energy so that the energy out of the light that passed through it would be different, and that would give us useful data. So energy in would not be equal to energy out. Now, depending on what we're looking for, there are different wavelength regions for light that would give us interesting results. So NMR that we'll rely on heavily, for example, is radio wave. IR, as it mentions, is infrared. We also have something called UV vis. And we'll talk about X-ray actually as a possible wavelength of light as well. All right, so why do we use spectroscopy? It's actually extremely important. So it helps us, as the first question posed, identify an unknown. It can also help us determine the purity of something we know. So we could acquire a spectrum of it, and if it looks like it should, then we can determine purity. So identity, purity, but also as when we move into reactions, we'll see that's a very useful tool to test the progress of a reaction. So if the reaction's not done, we'll see evidence of starting material present as well as product. Also, just to do a quick overview that we'll learn soon, is something called molecular spectrometry. Notice the suffix is different, and that's because this is the only instrumentation technique that does not use light energy. It actually uses a beam of electrons in order to affect the change that we're looking for in the molecule. But I'm putting this here because it is an instrumentation technique that's useful in the lab, and it helps us identify and ultimately deduce the molecular formula, which is a very powerful piece of information to obtain from a sample. IR spectroscopy, it gives us functional group information. So we will not know conclusively the structure by the end of this section, but if we have other hints, possibly from other spectroscopic methods or reference materials, the IR can help us narrow it down with the fact that it'll help us identify what functional groups are present. NMR spectroscopy is a very powerful one. We could have carbon or HNMR, and it can help us identify and conclude what the carbon skeleton looks like. We could figure out if it's branched or not, how many carbons are in there. So let's put that back, skeleton. And X-ray crystallography is very exact and is about as good as you can get with determining structure. It's almost like getting a picture of the molecule, but it's hard to obtain. You have to have a single crystal that can diffract X-rays. So it's not always feasible, but if it's possible to do, you can grow single crystals that are high quality. You can get the geometric locations of the atoms in space. So you notice this reference to all the different wavelengths of light, right, that we will be using. We're going to focus on infrared today, and so I'll point out a few things that infrared theory kind of relies on. So infrared spectroscopy takes advantage of the fact that molecules that have a permanent dipole, fill that in here, will absorb specific frequencies of infrared radiation. And that will be characteristic of their structure. So that gives us the functional group information. So what happens is when it absorbs the energy, it has to release some of it, and it releases it in the form of vibrational modes. What does that mean? It means the energy that went into the sample perturbed, otherwise excited, the state of that molecule in some way, and it had to release the energy, allowing the outgoing energy to be less because it actually released some with some way to release this perturbation. So for example, in IR, because it excites it and accesses its vibrational modes, it actually causes the bonds and atoms to vibrate to release the energy that it absorbed. So let's put this up here. There we go. So the types of vibrational modes that you'll hear reference to would be things like rocking. So they're motions that the molecule and the bonds make. Stretching, so the bonds themselves can stretch. And there's one that's called scissoring. So to visualize that, I'll just draw kind of a little quick sketch of what we might see. I'll draw a tetrahedral carbon, and I'll do an example for rocking, and I'm going to repeat this picture for stretching and for scissoring. So those circles just represent a group. That I'm not defining. So maybe I'll color it just so that's clear. So I could put so there's nothing, these aren't O's, for example. These are just generic whatever groups are attached. But what happens is the resonant frequency, term you might remember from physics, resonant frequency for the infrared region would allow the molecules to absorb energy so that their bonds would actually release the energy in the form of vibrational mode. So if they're to undergo the rocking action, you might see the rest of the molecule stay still except for these top two kind of wave back and forth in the same direction. Or they might stretch. This is not a dipole arrow. This means they're literally getting longer and shorter there. Please refer to the supplemental video I'm going to be posting. That's the 3D sort of rendering of this. That'll make it a little more clear. But this is the best I could do, like kind of on paper. Or they might scissor, or, you know, just like scissor handles, and the edges of scissors will go back and forth towards each other and away from each other. Okay, so I'm going to get into these specific energy values, and I'm going to ask you a question first. So what if I said, hey, what's new? And you could reply, if you're remembering anything from Physics 101 or Chemistry 101, knowing that E equals hc over lambda, right, which also equals h nu, then you could say, hey, nu equals c over lambda. So next time someone asks you what's new, you can have that in your back pocket ready to go. C over lambda is new. Or E over h, however you want to remove those around. But I'm bringing that up for a reason. We're talking about specific part of the electromagnetic spectrum, a specific set of energy values that correspond to the infrared region. They could be described with energy. They could be described with wavelength. They could be described with frequency. So you're going to see we have a preference of expressing it as inverse centimeters. It's kind of like 1 over the wavelength, but you might actually hear it synonymously described as a frequency range or an energy range. And that's because we're all talking about the same thing, energy of that light and where that applies. So to brush up your memory on what the infrared region really means, I'm going to remind you about the electromagnetic spectrum real quickly. So I had a mnemonic for it that always worked for me. Raoul's mother is visiting Uncle Xavier's garden. So in other words, that's radio waves, microwaves. Here we go. Here's our IR, infrared, visible, ultraviolet, violet, X-ray, and gamma. Now, you probably want to fully understand this in terms of why they're listed in this order. That has to do with their relative energy values. And also, furthermore, you want to remember that visible is an important range because that's when we see the color. And so this is the whole Roy G. Biv: red, orange, yellow, green, blue, indigo, violet. So that's contained within the visible light spectrum. Now, increasing energy or decreasing energy, who's the highest energy out of all of these? Hopefully you can think about the fact that gamma rays are harmful and X-rays are harmful. That's why those technicians wear those lead aprons and step out of the room when they're doing an X-ray. So knowing that these are actually harmful helps you remember that they're actually the higher energy part of the spectrum, as opposed to radio waves, which are, as far as we know, harmless. So we'll put a little label here. This is the area of high energy. This is the area of low energy. Furthermore, since energy is proportional to frequency, then we would also say high frequency, low frequency, but it's inversely proportional to wavelength. So high energy would be low wavelength, and low energy would be high wavelength. So just keep that in mind. Now, infrared is the focus of today. We will actually need to remember this for other areas of the spectrum that we work on. For example, when we talk about ultraviolet and visible spectroscopy, and when we get to NMR, we'll be talking about radio waves. So infrared is there. Now, taking a second to point out what's going on in the visible range, remember that this is red, orange, yellow, green, blue. Indigo and violet are really the same thing. I mean, that's purple, right? All right, so red appears just before infrared, and violet appears just before ultraviolet. So this is infrared's right before we start to see red, ultraviolet is right after we see violet. So it's not visible. It's usually like black light is what we're thinking of ultraviolet. So infrared is the energy source that we'll be using. And since our convention as chemists is to report this in inverse centimeters. You might, if in a physics class, report it as nanometers. But this is reported as inverse centimeters. That's how it works out to be in the 4,000, probably is our highest max that we'll ever look at, down to maybe 1,200, 1,000. But notice that the ones that you're going to be identifying frequently, and I actually do provide this chart on exams as a reference. It's allowed because, except for the final, because it allows you to identify what the functional groups are without having to memorize it. But you could see trends. So notice that we have OH is always going to be our highest frequency range that we can imagine, highest wave number is what that's called. So I'm gonna write wave number here so we can remember wave number. So that's gonna be on our x-axis. So let's see what an IR looks like. So there's acetone, and there are a lot of peaks there. And here's the annoying thing about IR is you actually are not supposed to identify most of the peaks. You have to find the peaks you expect to see and justify them. The extra peaks will be there beyond reasons that we're going to go into in this class. And so the way we're going to keep it kind of simple is to say, okay, well, if I have a known and I'm trying to explain what's there, I need to write out everything, even all the bonds. So that wasn't good enough job with acetone yet. I'm going to write out even more information. I'm going to write every bond because I'm trying to see, that's the nature of what happens with the IR spectra, is that it comes from the fact that the energy that was absorbed by acetone then resulted in acetone stretching and bending those bonds, and the energy out detected by the spectrometer was able to resolve that there was an energy difference that correlated to the IR region. And then the detector ultimately transforms that information into a plot that we can visualize. Now, I'm not going to be interested. Your book will show you lots of information about how it actually works for your own interest, mechanically speaking. We go into a little bit more of that in 212 with an activity where we can actually take one apart. But for now, we just want to interpret what comes out of the instrument. We're not going to focus on what the instrument itself is doing mechanically, how it was assembled, although it is interesting. Our important result is how do we use it to interpret what's going on molecularly speaking. So now, how do I use this information that I know I have acetone, and I've taken an IR spectrum? What about the IR tells me that, or confirms that it's really acetone? This is a big deal here. The carbonyl stretch is going to be one of the 2 or 3 you're always looking for. You'll pretty much memorize where those are in acetone. Look how strong it is. It takes up the whole length of the spectrum. And so this is absorbance. It could also be called transmittance. And this is wave number. And so if it's transmittance, the scale's reversed because it's the opposite. Absorbance is how much was taken out. Transmittance is how much passed through. So if it's absorbance, 0 to 100. If it's transmittance, 0 to 100, right? Wave numbers on the x-axis. Notice our range is 4,000 wave number. Usually below 1,000 is useless to us because there's not a lot of information other than what we call the fingerprint region. So I'm going to write that down here. Fingerprint region, which it's useful if you know what the fingerprint's supposed to be. Every molecule has its own fingerprint, and so every spectrum of acetone will have the fingerprint, right? However, it does not match anything we could predictably see. Say, hey, what does another ketone look like? Is the fingerprint the same? No. The fingerprint is unique to each and every molecule. So we can't make a trend based on a fingerprint region. Above the fingerprint region, we can find peaks that are meaningful. Now, this is my simplified list. If you go to another book, you're going to see pages and pages and pages of peaks. These are the ones that are the most popular. So I'll write that down more as a disclaimer, because if you're stuck on something, and this isn't giving you enough information, you can always refer to a longer list. I like to have a simple, shorter one for a quick reference. So this is kind of your quick reference list there. So fingerprint region is there. There's probably one other one I've added over the years, which is the CO stretch single bond. So that appears somewhere between, 1,200 to 1,000 centimeters, and it's usually strong. So notice what we're listing about the information here. The bond itself that absorbs the energy, where we'd find it along the x-axis, and then the intensity, which has to do here. So this would be a weak signal. This would be a approaching medium. When you get to halfway, it's about medium, and these would be strong. Okay, so now I'm ready to kind of point out what's important in the acetone spectrum. So we had this carbonyl. Notice if not the whole x-axis is labeled, but I could at least tell that this, if I have 1,500 here, 1,600, that's 1,700. Now let's see where that matches here. 1,700. Notice this says carboxylic acid CO, amide CO, aldehyde CO, ester CO, ketone CO. They all overlap. So you're not necessarily going to tell exactly which one's which. You have to be a little flexible. But the important thing is that all the different carbonyl functional groups fall between somewhere around 1650 to 1750. So right smack at 1700 is definitely a carbonyl. Very strong, very characteristic. So that matches what we predict for acetone. Now let's look at our other bonds. We have a CC bond and we have a CH bond. Let's look for the CC bond. OH, CH, NH, CH, 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 OH, CC. But this is triple bond C. This is CC double bond C. These are all COs, CN. So there's no single CC bond, and that's because there is no frequency absorbed for those bonds. So we don't see it. Let's move on to CH. Now CH, we see an alkyne CH. That's not this one. We see a vinyl CH or aryl. Remember, vinyl means on a pi bond. So that is a vinyl CH. Aryl CH would be on a benzene ring. That's why they're similar, because they're both H's that are on a carbon that's part of a pi bond. So that's still not the one in acetone. Acetone is a plain old alkyl sp3 CH. So that's this one, 2900 through 2850. So let's see if that matches. There's 3000, 2900, so just below. I should see a peak, and I do. So I'm going to circle those. It doesn't matter that it's weak. Okay, so I have 3 types of bonds, and I've identified them. This one, and this one's not in the chart. So I'm done with interpreting the IR. Yes, I don't know why this is here, or this, or this. These are left alone. You just ignore them. You only look for ones that you can identify. So here's another overview of the functional group zones. So you can have, see if I can turn this around. Turn it this way, there we go. So you can have look at the ones we've already assigned, the CO stretch zone. Okay, I like to, every time I get an IR, one of the first things I do is make this line. This is the 3000 line. And that tells me which kind of CH I have. Notice how there's 3 types of CHs, SP, SP2, or SP3CH. So here's my SP3CH, here's my SP2CH, and then way above that actually is my SPCH. Also way up high we have OH and NH. So when you see something at 3000, you can't say it's OH for sure. You have to have other clues to indicate that, unless it's got this particularly broad shape we're used to seeing. But NH is also broad, so those could be confused. But if you know the molecular formula, then you know which one to assign. Right here, it's pretty diagnostic, which means there's not a lot of other things that overlap there. So we can conclude it's one of the triple bond, CC or CN. And then alkenes show up here, higher 1600s, 1400 to 1600 aromatic. And here's those carbon oxygen stretches I was telling you about. The fingerprint region really begins here, and the only thing that also overlaps with the fingerprint region that's useful is the CO stretch. Okay, so spectroscopy is a lot of fun, I think. I think one of my favorite types of problems are spectroscopy problems where we have to figure out sort of the mystery molecules that, given all the right clues, if you studied it right, it'll feel like you're solving a puzzle, and it'll be actually quite satisfying. One of the major pieces of the puzzle that helps is this idea called degrees of unsaturation. So you have to do a little easy math to kind of work out one of your clues. And so remember, from day 1, we talked about saturated hydrocarbons. And we're going to take advantage of that formula. So saturated hydrocarbon, that formula has for CN, H2N plus 2, right? So in other words, 2N plus 2 equals the number of H's. So in other words, if a carbon has all of its bonds used to either bond to one other carbon or other H's, it'll satisfy that formula. So alkanes are saturated hydrocarbons, right? So let's see how the formulas satisfy the saturated hydrocarbon and how we can actually see whether it satisfies that or not. And the way that it will deviate will actually help us come up with the math formula that'll help us predict what's going on in the structure. So here's an example of a plain alkane, right? So it has 1, 2, 3, 4, 5, 6 carbons, so it's hexane, C6. But it could also be branched, and that would mean they're just isomers, right? So I'll write that down. So we're just looking at isomers. Constitutional, of course. And so they have the same molecular formula. No pi bonds. So that means they should have the maximum number of H atoms would satisfy 2N, where N is the number of carbons, plus 2. And it does. 6 times 2 is 12, plus 2 is 14. So that's a saturated hydrocarbon. Now let's look at an unsaturated hydrocarbon. That can happen by adding pi bonds. So notice when we add a pi bond, if you fill in all the H's, and that would be a good exercise to go ahead and pause this video and do that, and count them up. you're going to notice your H count is 12, not 14. So why would we get 12? 12 is because we, instead of having each one of these have a bond to hydrogen, we instead bonded a second time to carbons. So we had lost 2 hydrogens in the process. So we're off by 2. So the number of H atoms possible is off by 2. Add in another pi bond or a triple bond, which means 2 pi bonds, then we're off by 2 times 2, so 4. So in other words, each pi bond, this is a pattern we're going to see, decreases the number of hydrogen atoms by 2. Now, multiple bonds do this, but so do rings, and we will have seen that in our previous studies when we were trying to come up with other constitutional isomers, realizing that rings don't work. So once again, let's use hexane as our model, C6H14, that satisfies HCN H2N plus 2. As soon as we have to connect the ends to make a ring, we have to make another bond to these carbons. They're bonding to each other. That means we have to take an H off of each end to open up that degree of freedom. Now, what that does is mean that we remove 2 H's. So 1 ring removes 2 H's. 2 rings, and I urge you to fill in the H's on here to prove this to yourself, removes 4 H's. So, same idea. The degree of unsaturation can be obtained with rings, and that would decrease the total number of hydrogens possible by 2. Now, other things come into play. If we're not working with just hydrocarbons, what if we have some heteroatoms on board there? They don't have the same bonding pattern as carbon, but we could still get clues for what their formula means by looking at what happens when we replace one of the carbons with a heteroatom. So let's take this simple saturated hydrocarbon butane, C4H10, and let's see how we deviate from this formula by incorporating a heteroatom. So I'm going to put a nitrogen. So nitrogen, it could just go right in the middle here. Put the ethyl on each side. Notice by adding a nitrogen, since nitrogen makes 3 bonds, it wasn't sufficient to put it in the middle and leave the formula the same. It needed an H to fill its valency. So we added 1 more H because of nitrogen. So this is plus 1 H. But look at carbon. The hydrogen, this diethyl ether with oxygen, this ratio of carbon to hydrogen stays the same whether we have oxygen present or not. And that's because oxygen only makes 2 bonds. So it acts kind of like this little silent spacer that doesn't make any difference. So we will not need to change our interpretation of the bonding if oxygen is present. But look at the halogen now. So this will be true of all halogens. Notice that if we just put a chlorine on the end, we keep the number of carbons the same, we change the hydrogen count by 1, but this time instead of 1 more, it's 1 less. And that's because chlorine makes 1 bond. So it's like replacing an H. So in other words, we're short 1 H. So let's start to put that together. All right, I had that kind of cut off here, the same conclusion, but I'd written it on the previous page. So each nitrogen increases the number of hydrogen atoms by 1. Each oxygen does not affect the number of hydrogen atoms, and each halogen replaces a hydrogen atom, so it decreases that. You put that all together, and you'll get what's called the degree of unsaturation. So that could be DUN equals degree of unsaturation, or index of hydrogen deficiency. These are all the same thing. Unfortunately, they have a lot of different synonyms depending on which book or online source you're looking at. Deficiency. They're all saying the same thing, and you might see different ways of writing the formula, but it's C. So it's derived from the C number of hydrogens equals 2n plus 2 for a saturated hydrocarbon. Then it takes into account all of those. So the max number is 2n plus 2, but halogens and nitrogens play a role in the hydrogen count regardless of rings and pi bonds. Then we can put all of that information into the following formula. So C, number of carbons, plus the number of nitrogens divided by 2, minus H, counting the same as a halogen, so X equals halogen, H plus X over 2 plus 1. So that's because we divided by 2 because of this 2n plus 2. So n was the number of carbons, but if you divide by 2, you get C. And then we also accounted for the fact that nitrogen, we adds an H, so, but it's divided by 2 because we divide everything by 2. And then we're taking away how many H's there could be, but we're including halogen in the count since it makes one bond. And then that plus 1 came from the plus 2 divided by 2. And so that, what does that tell us? This equals the number of rings or pi bonds in a molecule with that formula. If you do this math and you get a negative number or a fraction, you did something wrong. So it must be non-negative whole number. And so carbon is the number of carbons. C equals the number of carbons. N equals the number of nitrogens. H equals the number of H's. X equals the number of halogens. Okay, so let's do some examples. Benzene ring. How many degrees of unsaturation does a benzene ring have? We could do this two ways. We actually know the structure. So we could say, well, I'm not drawing the structure. It has one ring and 1, 2, 3 pi bonds. So it should be 4, right? Because that equals 1 ring plus 3 pi bonds. What if I didn't tell you the structure of benzene? I said, hey, benzene C6H6. Let's use the formula. So, okay, number degrees of unsaturation, DUN, equals 6 plus 0 nitrogens over 2 minus 6, 0 plus 6, because there's no halogens, over 2 plus 1. All right, so 6 over 2 is 3. 6 minus 3 is 3 plus 1 equals 4. So that's how that works. Since benzene rings are so common, whenever you see degree of unsaturation greater than 4 and you have at least 6 carbon atoms, you most likely have a benzene. So it's a really good idea to consider it when you're trying to guess what the structure is. Other ways you can check for benzene rings, we'll look at the other spectroscopic techniques. And that will be something that we cover in short amount of time, but NMR and mass spec, IR. So IR obviously is one we're covering today, but in the future NMR and mass spec will help with those as well. So we can figure out the DUN from the structure or the formula. So if I said, hey, draw me a structure that has 4 degrees of unsaturation. Can you tell me if it would have a benzene ring and an alkene? Well, let's look. Let's draw a benzene ring with an alkene. Well, we already know that benzene is worth 4 DUN. An alkene is 1 DUN. So total would be 5 DUN. So this would, if we had 4 degrees of unsaturation, then this would not be allowed. So you should always do a little common sense check to see what all your evidence told you, and then decide if you drew something that's actually valid. Let's do another one. This is actually pretty powerful, this DUN, because we can come up with a reasonable structure. What's the most likely formula for C7H8? Okay, so let's calculate the DUN. That's what you always want to do. If you're given a formula, you get the DUN right away. So I'm going to write that out because that's a huge deal. Formula given, find DUN. That's a gift if you're given the formula. It's not always happening. So let's do the DUN. DUN equals C7. So 7 plus 0 nitrogens over 2 minus, there's no halogens, but there are H's. 8 over 2 plus 1. Okay, so this becomes 4. 7 minus 4 is 3. Plus 1 is 4. Okay, so 4 DUN. Okay, so what did we say? We said, well, if you have more than 6 carbons, which we do, and you have a 4 DUN or more, then let's try benzene. That's the most reasonable thing to start with. That'll knock out 4 DUN. Okay, so that's C6H6. Now we have one more carbon left to deal with. It could only be a methyl. So if you count your hydrogens to make sure, we have 5 H's on the benzene ring, plus 3 is 8. So that satisfies C7H8. That's a huge deal. I mean, think about that for a minute. You were just given a formula and you got a structure that is pretty reasonable. And so that's actually most likely the structure. When you couple this with a spectroscopic technique, you could even make this approach even more powerful. Here's a real IR obtained in the lab, and you're going to solve the mystery structure. You're given some information. Always read the problem and assume that there might be a good clue in there. Compound has the formula C3H8O and the following IR. What's the structure? Annotate all the peaks by making an IR table. So I'm going to show you how to make an IR table because we will be doing that in our lab reports. So you need to have the wave number, and that's in inverse centimeters for your units. And you need to write out the bond that's responsible for it and be prepared to have several entries. So in a lab report, you'd enter it as a table. We're given this information. The formula equals C3H8O. What did I say you have to do when you find the formula? You must get the DUN. Okay, so we're going to say DUN equals 3 carbons, and we have no nitrogens. Halogens, we have 0 halogens. We have 8 H's over 2 plus 1. All right, so this is 0. This becomes 8 divided by 2, which is 4. 3 minus 4 is -1. -1 plus 1 equals 0. So that means we have no rings, no pi bonds. That helps. So now we can come up with the different ways to put together 3 carbons. So we could have all the carbons connected and then an O at the end. And that O, of course, has to have an H. So let's just see if we satisfied our formula by filling in our H's. So we have a 3, 4, 5, 6, 7, 8. Yep, this one works. C3H8. O. Or we could have had the oxygen in the middle instead of at the end. And we could have a methyl on one side and an ethyl on the other. So we either have an ether or an alcohol. Oops, I think alcohol. There we go. So we have not enough information to decide from here, from the formula alone. So we're going to go to the IR. Now, if we have an ether, we should see a CC stretch, or CO stretch, CH stretches that are sp3, and we should see a CO stretch. If we have an alcohol, we should see a CO stretch, so that's the same as this one. We should see CH sp3 stretches with the same as this one. So far, nothing to distinguish it. But wait a minute, we'd also see an OH stretch, and that is one of the most diagnostic peaks, which is why it's an example here. In addition to the carbonyl peak, the OH peak is probably equally important. So if we go back to our chart that tells us the wave numbers, we'll see at around 3400, we have the really broad OH peak, and that's this one. So that tells us, voila, we have an alcohol. So thanks to this OH peak, it's called the OH stretch, we have confirmed that we have an alcohol. So we need to fill out our chart. What kinds of bonds do we have? Well, we have the OH. We know that appears around 3400. Use the number that's already printed on there for you. That makes it easier, 3341. That doesn't always happen. If it doesn't, I just take the middle of the peak and kind of follow down to the x-axis and get my best approximation. Remember, one of the other things I like to do right away is sometimes get a ruler if I'm doing this by hand, and do a 3000 line right there. Anything to this side immediately is sp3ch stretch. So that's what these are. So I'm going to fill those in. We know we have to be finding a ch stretch, and there's two labeled, so I'll use them both, 2974 and 2885. And finally, the last type of bond in my alcohol is a CO stretch. And those are around 1200, or between 1000 and 1200. So right there. And there's usually two of them. They're like twins almost. So I see one at 110001 and then 1009. Okay, there's my IR table. That's required to fill out along the way. And so get the hang of doing that when you do IR problems.